Good afternoon, and it is time to learn a new data structure. So I'm going to come up here and say a new data structure. And this wonderful new data structure are called trees. And I'm going to take a guess that you've probably seen trees before, but we're going to be looking at them in much closer detail now. So the question is what is a tree? And we'll spend a little time on that. What is a tree? And before I answer what is a tree, I have a related question. What is a graph? And perhaps some of you are taking the class in discrete mathematics. I don't remember the number of that class. I think it might be Computer Science 314. But we know that a graph, to be very formal, is a graph is a bunch of vertices and a bunch of edges. So that we might come over here, and here's a vertex, and here's a vertex, and there's a vertex, and there's a vertex, and there's a vertex, and we might even give these names A, B, C, D, and E. So V would be equal to the set A, B, C, D, and E. And then some of these might be connected. So this might be connected to that one there, and maybe this one is connected to that one there, and maybe this one is connected to that one there. And maybe that's what it looks like right over there. So we have a bunch of edges here. And in this case, we're gonna note that there's an edge from A to B, and in this case, there's no orientation. So the edge from A to B is the same thing as the edge from B to A. So we might denote that edge over there as AB. Okay, and notice we've used the set notation there because that would indicate that there's no difference between that and that. And maybe we might even be a little bit more clever here, and we might give that edge a name, and we would call it E1. And over here we might have AE, which is equal to EA, and we would call that edge epsilon 2. And over here I've got this set DE, which is equal to ED, and we would say that that's equal to edge E sub 3. So we'd come over here, and now I'd have my set of edges, and we might say, well, that's equal to E1, E2, and E3. So this over here defines a graph, okay, and it defines this particular graph that I have drawn over here. We'll give you some quick definitions here. This is much more important probably in your discrete math class than it is here. But let's consider a graph that looks like the following. And maybe this graph looks like this. Okay, so this is a graph over here, and we will say a graph G is connected if and only if there exists a path from every vertex to every other vertex. So we can see in this case over here, there's no way to get from this point over here to this point over here. So this particular graph that I have drawn is not connected. On the other hand, we can see that this graph up here is connected. Okay, I can get from any point to any other point. There's a path. I can go from A to D, I can go from D to B, I can go from E to B. There's no problem here. So this is connected. This is not connected. Okay, so that's one definition that we need. Another definition that we need is let's consider a graph that looks like this. Okay, and the thing that I want you to note about this graph here is I can start at this point here, and I can travel up this way, and then I can travel this way, and then I can travel this way, and this way, and this way, and I end up right back where I started. Okay, this is what's known as a cycle. Okay, and a cycle is a finite path. Okay, that goes back to where it starts. Now I got to be careful here because that's a bad definition. I could come over here. Remember we said there's no difference between this edge and this edge. So we could say, well, gee, I could go up to here and then I could come back over here. Okay, and that would give me a cycle, but I've used the same edge. So I want to say that a cycle is a finite path, and I'm going to start adding to this. That contains unique edges. That goes back to where it starts. So these are not unique edges. These are the same edge. Okay. So finally, I can say that a tree is a connected graph with no cycles. So here's an example of a tree. Okay, we can see that it's connected, and we can see that there are no cycles. Here, this is a tree. This is not a tree. It's not a tree because it's not connected. Here's something that's not a tree. Okay, not a tree. And the reason why it's not a tree here is because there's a cycle. Okay, so now we're up to trees. So now we have to talk about what is a binary tree. Okay, so a binary tree, this is a tree where every node, and remember node is just another word for vertex, has at most two nodes connected to it. two nodes binary. So here's an example of a binary tree. Got a node. I'll connect 2 to it. I'll come over here. I'll connect 2 to it. I'll connect 1 to that. I'll connect 2 to that. And I should say over here, at most 2 child nodes. If we want to think of whatever is up as a parent and down as a child. So I come over here. There's one. So we can see over here, first of all, that this is connected. We can see that there are no cycles in it. And if we pick out any node, we can see that any node has at most 2 children. Some of them only have 1. This is a binary tree. And lastly, a binary search tree well, what a binary search tree is a binary search tree is a binary tree and it's got values in each node. Now those values could be names, they could be numbers. And it satisfies the following property. For any node all subtrees to the left are less than or equal in value. To the right, they are greater than or equal in value. And normally we'd actually just say less than and greater than, and we'll take a look at what we mean by the times there might be equality. So let's again consider an example. And let's suppose I'm going to create a binary search tree, and I have a bunch of names that I'm going to create. So maybe there'll be Mary, and then there'll be Chuck, and Sue, and then there'll be Ben, and then there'll be Al, and there'll be Roger. So we start off, there is usually something called a root pointer. And when the tree is empty, this just points to null. And now we come in there and we insert Mary. So here's Mary. And what's going to happen is we're going to find that nodes in a binary search tree are going to be made up of 3 components. And there's going to be the component where we store the data. And then there's what's going to be called the left pointer and the right pointer. So after we insert Mary, this is going to be null. And that's going to be null. And now we come along and we want to insert Chuck. So what's going to happen here now, okay, first of all, binary search trees always grow at the bottom, and you'll see exactly what that means right here. So I come over here, and here's Mary. And now it's time to insert Chuck. Well, Chuck is less than Mary, so this pointer over here still remains null, but this pointer is now going to change, and I'm going to insert the new node here. And here's Chuck. And now he's pointing to null, and he's pointing to null. And now what's going to happen is I'm going to insert Sue. So I've got, here's Mary. And now Mary is pointing to the left at Chuck. And that's null. And that's null. But now over here on the right, this is now going to point at Sue. And that's null. And that's null. So finally, we're going to come over here and we're going to insert Ben. So first of all, the thing to note is notice whenever I insert a new element in the tree, it always happens at the bottom. Okay? What's going to happen is some null reference is going to be changed to this new pointer. So I come over here, and here is Mary. And I'm going to come over here, and here's Chuck. And now I've inserted Ben. So here's Ben. And I think you can see after Ben, I would be inserting Al. So Al would now have null pointers down here. Let's see, before here, I had Sue over here. Okay, and I have to insert Roger. So here's Roger. This is null. This is null. This is null. So this is what this tree would look like after I insert these elements, just like this. And the way that I would come in here and I would do a search, suppose I'm looking for Ben, I would come in here and I would have some variable called rover, and I would set it equal to root. So initially it's pointing there. And if I'm looking for, say, I'm looking for Ben, I would go, well, Ben is less than Mary. So now I'm going to update rover to come down to here. And I go, well, Ben is less than Chuck, and I would update rover down to here. And I'd go, aha, I found the one that I'm looking for. I would return rover. Okay. The advantage of binary search trees is you can see that if you're lucky, this thing's going to be kind of balanced. Now, this particular tree here is really not that balanced, but what I want you to do is I want you to compare that with the following. Let me get this out of the way. Let's consider the same binary search tree now, but let's suppose that the names came in this way. Suppose they came in Mary, and then they came in Sue, and then they came in Chuck. So I've got Chuck and Sue, and then let's suppose we had Ben, and let's suppose we had Roger, and then we had Al. So I'm going to get Mary over here, and I'm going to get Sue over here, and I'm going to get Chuck over here, and then I'm going to get Ben over here. Oh, this still doesn't work out well, does it? And I get Roger over here. Okay, and I'll tell you what, instead of this being Al, let's suppose that this is Dave. Now if I come over there, this is Dave. Okay, this, what you're seeing right here, this is a balanced tree. On the other hand, suppose I came over here and suppose the names came in the following way. Suppose I had Ben, and then suppose I had Chuck, and then I had Dave, and then I had Mary, and I had Roger, and I had Sue. Same names, but you can see what's going to happen over here is I'm going to get Ben, and then what's going to happen over here is I'm going to get Chuck, and then I'm going to come over here and I'm going to get Dave, and then I'm going to come over here and I'm going to get Mary, and then I'm going to get Roger, then I'm going to come over here and I'm going to get Sue. Null, 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 null. So I think you can see what would happen here. Now there's 1, 2, 3, 4, 5, 6. If I were going to come over here and do a search for a name, in the worst case, I would have to look through all of these. Okay? For example, suppose I'm trying to figure out if Tom is here. If I'm trying to figure out if Tom is here, I've got to read through all n of these. Okay, here n is equal to 6. On the other hand, over here, to find out if Tom is here, you can see that I really only have to go here, and I have to go, well, there's nothing greater than Sue. So we can see over here that when the tree is balanced, we can see that search, I'm going to get big O of n is equal to log base 2 of n. But that's in the balanced tree. In the worst case, this thing degenerates into a linear search, and I would get that order n is just equal to n. So a lot of research has focused on rebalancing trees. There are some very desirable properties if you can keep the tree balanced. And later on this semester, we are going to take a look at what are called balancing trees. We're going to look at these things called red-black trees that attempt to keep themselves balanced. So it's going to take a few videos to describe binary search trees, and this is still the first video. We're going to keep it, well, it's already pretty long. I think it's about 20-25 minutes, and I'm going to guess we have about another 15 minutes to go. But first of all, we have to talk about the definition of our nodes, and actually you're going to find that our nodes are not too different than the kinds of nodes we had in our double-ended data structures, our double-ended linked list. So a node here for us is going to look something like the following. We're going to see that there is over here, we're going to have something that, this is going to be a node, a reference, and we're going to call this left. Over here, we're going to have a node over here, and we're going to call this right. Okay, so you can see left and right. And in here, we've put something called name, which in this case is a string, but we could make what's in here a much more complicated data structure. For example, in program number 3, this is actually going to be composed of two things in here. There'll be the key, which is a string, and then there is going to be the int that we're calling where. Remember, this structure was almost identical to the one you used in program 2, and you'll use it in program 3. And again, over here, there'll be a reference here and a reference here. So other than that, this is pretty straightforward. We have a constructor over here, and the constructor takes a string, and we create a new node where we put the string into name, and we set the left and right references to null. We have a public string toString, which would just output the name here. We have a get name and set name, so we have a getter and setter for this. And then we have our getters and setters for the left node and for the right node. So this is pretty straightforward over here. Then we come over here and now we're going to declare our class called BST. I guess I should have said public class. Okay, I think I made a mistake here, but you're all smart and can figure it out. And this is just made up of this thing called root, and our constructor over here just sets root to null, like that. That's the constructor. And in this particular video, I said I was going to write two methods. We were going to write a note to find, and we're going to write a note to insert. So first of all, let's just talk about find. It's pretty simple. Here's root, and we come down here, and we might imagine here's Mary. We come over here, here's Dave. Maybe this is Al. Maybe this is Ed. Over here is Sue. Roger. Tom. So we can imagine that we're coming in here and we are trying to find Ed. So here is my key. ed. And you can see that we have this thing called rover, which we initialize to the root. So if we initialize it, it's pointing at that. And we say while rover doesn't equal null, and then ultimately we're going to return rover. Notice what we're doing is we're returning an actual reference to the node that we're trying to find. So let's consider the pathological case first. Let's just assume that root is null. So if root is null, then rover's been set to null. And we would come over here and it says, well, rover doesn't equal null. Well, it is null in case the tree is empty, and I would return a null. So if I come in here and I'm looking for a key and the tree is empty, then there's no problem. It returns null. That makes perfect sense to me. So I come over here and I say while rover doesn't equal null, and I come over here and I do a compare value. Okay, so what I'm doing is rover is now looking at Mary, and I'm comparing Mary and Ed. And we note that Mary is greater than Ed. So if Mary is greater than Ed, then the comp val should be positive, and that would indicate to me that rover is equal to rover.getLeft. So what I've now done is I've updated rover to point to Dave, and I come over here, and I would go back up to the top, and rover is not equal to null, and I go if I compute the comp val, and I'm comparing now Dave and Ed. And now at this point, I know that Dave is less than Ed, so the comp val at this point is going to be, what is it? It's going to be positive. Is that correct? Okay, so I'm going to be comp val equals rover.getName compared to key. Did I say that correctly? When Mary was greater than this, I went to the left. Now what's going to happen is this is less than that. I'm going to move to the right. So I come down to here, and now rover is looking at that one. I go through the loop one more time. Excuse me. While rover doesn't equal null. Well, it's not null. I'm going to do comp val is equal to rover.getName compared to key. At these points, they're the same. So if the comp val is 0, I'm break, and I'm going to return rover, I'm returning the reference to here. Everybody get it? Suppose instead that my key was this, Eddie. Now at this point, if it were Eddie, I would come back up to the top, rover's still not null, and I would do this. I would say comp val is equal to rover.getName compared to key. So I'd be comparing Ed to Eddie. Okay, and in that case, okay, in case you didn't know, Ed is less than Eddie. Okay, so I would come over here and I would say rover is equal to rover.getRight. And that would be this null pointer over here. Okay, at this point, rover is equal to null, and I would return a null value. So it works there as well. Okay, find works. Okay, finally, for this video, the last thing we want to talk about is insert. Don't pay any attention to this for the moment. Let's come over here and draw a picture. So I've got, here's root, and here's Mary, and here's Dave, and here's Sue, and here's Alice, null, null, Roger, Tom. Okay, so let's review a couple of things about inserting a new node. So I've got some new node in here. I'm coming in with a new node. And maybe, oh, I don't know, Bill. Good name. And I want to insert this. So the first thing that you need to remember is remember that insertions are always going to occur down at the bottom of the tree. So this is going to go somewhere down here on the bottom. And in fact, we can see where it's going to go. I'm going to go from Mary to Dave to Alice, and I'm going to go to the right here, and I can see that it's going to be this one right over here that ultimately is going to be where it's going to reference Bill. But now here's the other thing that you need to remember. You might think that this is sort of like find, and it is like find. So you might think, oh, I'm going to come over here, and I'm going to declare this variable called Rover, and I'm going to initialize it to Mary. And what's going to happen is first it's going to point here, and then I'm going to update it, and it's going to point down here to Dave, and then I'm going to come over here, and then it's going to point to Alice, and then finally it's going to come over and it's going to be this value here. And when it's this value here, I've got myself a big problem. Because what I need is I now, at this point, I need a reference to Alice, because I need to change something in Alice. Okay, so I just can't have this single thing that's traveling down here, down this tree. And this might remind you, and it is very similar to, inserting into a linked list where I actually needed to have two references. Okay, let me just erase this, and I will draw you a picture to remind you of what was going on there. That's erased enough. Okay. What's going to happen here is I've got Alice, and I'm going to need a reference here. I'm going to need two references. I'm going to call one previous, and I'm going to call one current. And current's going to be just like Rover. So at some point, this thing over here is null, and what's going to happen here is we're going to have that current is also going to be null because it's pointing at the same thing. But at that point, I'm going to have a variable over here called previous, which is pointing here. And here, the final insertion would be, I would want to say something to the effect that previous.set, and here it's on the right side. I would want to do this to new node. Okay. So I think you recognize I'm going to need these two variables over here. So I'm going to have a node previous, and I'm going to have a node current. And I think you can see that I'm basically going to do something like the following. I'm going to set previous equal to null, and I would set current equal to root. And then I think you could see that the basic loop is going to look something like this. While current doesn't equal null, and I've got to do something in here, and we'll fill this in a second. But once I'm done with this loop, okay, then I need to come down here and I go previous.setRight new node. So the insertion occurs down here. But now you might be asking yourself, set right. How do I know whether I set right or whether I set left? And that's a very good question. What we're going to do is we're going to maintain a Boolean variable, and the Boolean variable is going to be called went left. And what happens is whenever I go down a left subtree, I'm going to set went left equal to true. And whenever I go down a right subtree, I'm going to set went left is equal to false. So basically, when it comes up here to finally do the insertion, I just look at the value of went left. If went left is true, I would do a set left. If went left is false, I would do a set right. Does everybody follow that? So we can even now start to think a little bit more. I think I can move this over a little bit here. About what this loop in here looks like. while current doesn't equal null. And what I'm going to do is I'm going to come in here and I'm going to have this variable. This is just like before. I'm going to say comp val is equal to current.getName dot compare to key. Okay, so I'm comparing what current is looking at. I'm comparing it to key. The other thing I'm going to do over here is I'm going to come over here and I'm going to say let previous equal current. And then I'm going to come over here and I'm going to say if comp val is less than 0. Well, if it's less than 0, that means that the current one is less than the key and I want to go to the right. If I want to go to the right, that means that went left is false. And I want current to equal current.getRight. Else went left is equal to true. And current is equal to current.getLeft. Well, this is kind of a mess, and that's okay, because I have created a cleaner version of it right over here. So let's take a look at this. So first of all, I come in with a key, I create the new node. I have these two nodes here, previous and current, this thing called comp val, and this Boolean went left is false. So the first thing I do over here is I just check to see if it's an empty tree. If it's an empty tree, I just go ahead and I insert the new node and I'm all done. Otherwise, I come into this loop here and I say while current isn't equal to null, over here, first what I'm doing is I'm comparing what current is looking to and I'm comparing it to the key set previous to current. If the comp val is less than 0, that means that what current is referencing is less than the key and I need to go to the right. And I set went left equals to false. Otherwise, I want to go to the left and I set went left is equal to true. So here is right over here, here's my whole loop right here. When I exit this loop, that means that current is null. I'm down at the bottom of the tree. Just like I'm getting ready to insert Bill, I'm right over here. And now previous is looking at Alice, and in this situation over here, went left is equal to false. So if went left, well, this would set the left one, else I'm setting the right one, which would be this one right over here. And I would actually be executing this line right here. So that is how I accomplish insertion.